every game has a Nash equilibrium, but in general, we do not know how to efficiently compute such a Nash equilibrium in a game. In fact, there are some indications that this may be a computationally hard problem to which we should not be expecting an efficient solution. However, there is at least an algorithm for two-player games which appears to work well in practice. The bad news is that, in the worst case, this algorithm also has an exponential running time. But in practice, it tends to find Nash equilibria quite quickly. I will introduce this algorithm, which is called the Lemke-Howson algorithm, over the next 3 videos. In this video, I will start by introducing the concept of a best response diagram. I will use a specific two-player game as a running example. I believe Bernard von Stengel from the London School of Economics and Raoul Zavani from the University of Liverpool have introduced this particular example to me, or at least an example very similar to this. And of course we could use any game as an example, but this one results in pictures that are relatively well arranged and help illustrate the algorithm. So I decided to just use these particular payoff matrices as well for my purposes. So this game has 2 players, as I said, and the first player has 3 strategies and the second player has 2 strategies. And the payoffs to the first player are as follows, and the payoff matrix of the second player is this. And what we now want to do is we want to write down or draw the best response diagram for the first player. Now, for each mixed strategy of the second player, we want to know which pure strategies of player 1, so strategy 1, 2, or 3, are best responses to that particular mixed strategy of the second player. So first of all, we need to be able to depict all the different mixed strategies that the second player has. And we can do this by simply drawing a line. And then the left end of the line is the point where the probability of playing strategy 4 is 0, and the right end of the line is where the probability of playing strategy 4 for player 2 is 1. And of course we can also indicate what the probability is of playing the strategy 5, and this would be 1 minus the probability of playing strategy 4. So this is sort of an error going in the other direction, where on the left end we have the probability of 1 of playing strategy 5, and on the right end we have a probability of 0 of playing strategy 5. Okay, so because these errors just go in opposite directions, we actually only need this one line, and we just remember that on the left side, player 2 is playing strategy 5 with probability 1, and on the right side, player 2 is playing strategy 4 with probability of 1. Okay, so now the y-axis in this diagram will be the payoff that the player receives. And when I say the player, I mean the first player of the game. And we now want to indicate for each of the mixed strategies of player 2, so for each point on this line, we want to say what is the expected payoff that player 1 gets when player 1 plays her first strategy, so strategy 1. Okay, so if the second player plays strategy 5 with a probability of 1, what is the expected payoff for player 1? Well, the payoff matrix of the game tells us the expected payoff is 3. What about the other side? So if player 2 plays strategy 4 with a probability of 1, what is the expected payoff that player 1 would get by playing strategy 1? Well, it would also be 3. There's no difference. So the payoff would in fact always be 3, no matter what the mixed strategy of player 2 is. So that happens when player 1 plays strategy 1. Now we can do something similar for strategy 2. So what happens if player 1 plays strategy 2? Well, if the second player plays strategy 5 with probability 1, then the payoff is 5. If, on the other hand, the second player plays strategy 4 with probability 1, then the expected payoff will be just 2. And then in between, we just linearly interpolate the expected payoff. So it's just going to be a straight line from 5 on the left to 2 on the right. And that's the expected payoff for player 1, depending on the mixed strategy of player 2. And we do the same thing again for the third strategy of player 1. So we just say, well, if player 2 plays strategy 5, then we get a payoff of 6. If player 2 plays strategy 4, we get a payoff of 0. And then in between, we just linearly interpolate to get the expected payoff. Okay, so these are the expected payoffs for the 3 strategies of player 1. Now, what would player 1 want to do? Player 1 wants to maximize the expected payoff. So if player 1 knows what player 2 is doing, player 1 would just pick the pure strategy that maximizes the payoff. So it would just pick the strategy that corresponds to the line that is highest in this graph. And so that depends on what the mixed strategy of player 2 is. But if we want a single function that describes this, we just take the upper envelope of all of those 3 lines. So this is just the maximum over all pure strategies I of the payoff matrix of player 1, which we call A, and multiply it with this vector y, which is the mixed strategy of player 2, and then the ith component of that vector. Okay, so now we know for each mixed strategy of player 2 what the best response of player 1 is. If we are on the left side of this line, in the left third of this line, the best response is playing strategy 3. And then if we are in the middle, the best response is actually to play strategy 2. And if we are on the right, then the best response is actually to play strategy 1. And we simply write this down. And in fact, what the exact payoffs are and so on will no longer be interesting to us. And so I will just remove this part of the picture. And we are left with what is basically the start of the best response diagram for this player. It tells us for each mixed strategy of player 2 what the best response of player 1 is. And there's one particular thing I want to note here, that there are certain points on this line where there are actually 2 strategies that are best responses. And those are the points where these labels touch. So right in between 3 and 2, there's a point there. And that's the point where strategy 3 and strategy 2 are both best responses because they give the same expected payoff. Okay, this was for player 1. We do the same thing for the other player. In this case, it's a bit more complicated in the sense that I have to draw 3-dimensional pictures because player 1 has 3 pure strategies. So the strategy simplex is a triangle in this case. And the meaning behind this triangle is that the lower left corner, for example, would mean that strategy x1 is played with a probability of 1. And in the lower right corner, strategy 2 is played with a probability of 1. And then in the corner at the top, strategy 3 would be played with a probability of 1. And then the points in the triangle are some mixtures of those pure strategies. And then we can again draw the expected payoff for both of the strategies of player 2. So let's start with strategy 4. What is the expected payoff of the second player? Well, if the first player plays strategy 1, the payoff is 1. If the first player plays strategy 2, then the payoff is 0. And if the first player plays strategy 3, then the payoff is 4. So we have these 3 corner points, and then all the other expected payoffs are just linear interpolations of those 3 points. So we get a nice plane that expresses our expected payoff for each mixed strategy of player 1. And then we can do the same thing for the other strategy of player 2, which is strategy 5. And so we just get this second plane here, which expresses the expected payoff for strategy 5. And we notice that these 2 planes intersect, and that on the left side of this picture, the plane that corresponds to strategy 4 is higher, and on the right side of this picture, the plane that corresponds to strategy 5 is higher. And so, again, we are not interested in the actual pairs, we just want the best response regions. So we want to divide the mixed strategy simplex of the first player, so this triangle, into the regions where 4 is the best response and the areas where 5 is the best response. And we know this now. On the left side, there's 4 is the best response. On the right side, 5 is the best response. And then there's a line where this 4 and 5 touch, and on this line the expected payoff is the same for both strategies, and so both 4 and 5 are best responses. And this is almost what a best response diagram is, but I will add some additional labels to these 2 best response diagrams now. And the reason for this will become clear in a minute. So we add labels to indicate that a pure strategy of a player is played with a probability of 0. Let's look at the left picture. We remember that on the right-hand side of that line, we play strategy 4 with probability 1 and strategy 5 with probability 0. And so on the right-hand side of this line, I add the label 5, because there strategy 5 is played with a probability of 0. And on the left end of the line, it's strategy 4 that is played with a probability of 0, so I add the label 4. And on the picture on the right, so the best response diagram of the second player, I have something similar. There, it's not a single point where particular strategies are played with probability 0, but it's an entire line. So the line, the diagonal line from the top corner to the bottom right corner, on this entire line, strategy 1 is played with probability 0, because it's played with probability 1 on the opposite corner, right? And then on the line from the top corner to the left corner, it's strategy 2 that's played with the probability of 0. And then at the bottom, it's strategy 3 that's played with the probability of 0. So I add all of those labels. And now we are finally done. These are our best response diagrams. Okay, why did we do this? Well, because now we can essentially read off these diagrams the Nash equilibria of the game. So you have to realize this. A strategy profile is simply a mixed strategy for player 1 and a mixed strategy of player 2. And so a strategy profile is just a point in the left diagram and in the right diagram. And if we have a pair of points, that's a strategy profile. And the question is, when is such a strategy profile in Nash equilibrium? And the answer is, if each player plays the best response to what the other player is doing. Okay, what does this mean? Well, we remember that something is in Nash equilibrium if each pure strategy of a player is either played with probability 0 or is a best response to what the other player is doing. And that means that we need to find all the labels in this pair of points. So I have indicated a pair of points here. And on the left, you can see this particular point where both strategy 2 and strategy 3 are best responses. But strategy 1 is not. Okay? Now, on the right side, I've indicated a point for player 1. It's a mixed strategy for player 1. And at that point, strategy 4 and 5 of player 2 are best responses. Now, that means 4 and 5 are best responses, and 2 and 3 are best responses, so almost everything is a best response. But what about strategy 1? Strategy 1 of player 1 is not a best response. So for this to be a Nash equilibrium, it means strategy 1 has to be played with a probability of 0. Is this the case? Yes, it is, because the point on the right-hand side actually touches label 1. Right? It lies on this line where strategy 1 is played with probability 0. So what do we observe? We observe that for this pair of points, we see all 5 labels. We have label 2 and 3 on the left picture, and we have label 1, 4, and 5 on the right picture. So we get 1, 2, 3, 4, and 5. And that means this is a Nash equilibrium. This is what we are looking for. We are looking for a pair of points in these two best response diagrams such that they touch all labels. Nash equilibria exactly correspond to fully labeled pair of points in these best response diagrams.